question about the survey.
Uh-huh.
Is it supposed to look like this?
No, that's the wrong survey.
Right.
Good point. So Evasys, that's the end of module survey that you'll do at the end.
Right.
I'll say more about that when it's closer to that. So it should be under quizzes. It's just set up as a normal quiz. The Evasys survey is a bit more higher impact if you want. That's our official evaluation that goes into how changes are done for modules and courses. It goes into evaluations for staff. We'll talk about that in more detail. That's also a bit more extensive than this one. The midterm survey, what I meant to do was to send you a link in that email on Canvas. Maybe check your email if you've received that. But I don't want to discuss this today anyway, so we might as well postpone that for Wednesday. Gives you a bit more time. The purpose of the midterm survey is to have a little quick checkpoint of how things are going from your perspective while we still can change something. The end of module survey is brilliant to iterate and improve for the next year, but that doesn't help you guys anymore. And so, I mean, there's this term of survey fatigue, which is a serious thing. So we don't want to overburden you with too many questions. That's why the midterm survey is really, really quick. And it's just an invitation to discuss some things that go or don't go well at this point. Okay, I'll double check if the link was in the email. If it was, check your email that you should have received today, earlier today. There should be a link, and it's just set up as one Canvas quiz. So if you go to quizzes on Canvas, you can fill it out. However, don't do it now because I need your full attention for parallel sorting. Let's go back to that. Okay. We left off last time discussing these building blocks for parallel algorithms. We spent much more time last time talking about parallel algorithms in general. I don't want to recap all of that, but I want to show this slide again at least, because that's the key building block we will use, or the more abstract version, the parallel prefix sum. So again here, the idea was you have an array of things, and you can, for example, parallel prefix sum, you can compute all the partial sums. For every element, you sum up what's left of it, including that position. And that might sound weird, but you can do this efficiently parallel. You can do this with log n parallel time and linear work, as you've seen last time. And one simple way to use that is this little piece of code that will actually appear literally as part of one sorting algorithm later. You can use that to compact a sequence, take out a subset of the positions, and put them into an array. Any questions on this? Again, the memories come back after the long weekend of bamboo cutting and all that. Just to show the key picture was my messy way to explain this. That's the parallel prefix sum algorithm before we made it work efficient, and then the work efficient version was this cutting things into blocks. Oh, that wasn't what I wanted. That picture was going from the work inefficient but fast parallel time algorithm to the final result that we used later, namely log n time linear work. In the next subsection, we finally put this all together for parallel sorting algorithms that use all these primitives that we've built up and go much beyond what we've seen initially for parallel string matching, where we could get away with just these very simple tricks of parallelizing. This time we'll have to try a little harder, but the algorithms that come out are much more interesting. We'll look at the two key algorithms we discussed in Unit 3, Mergesort and Quicksort. So let's look at Mergesort and think about how can we do what Mergesort does in parallel, doing it on our PRAM. One thing that's easy, Mergesort, remember, divide and conquer and all that, it had these recursive calls. You first sort the first half and then the second half, and then you merge the result when these recursive calls come back. Because the two recursive calls work on a disjoint part of the input, you can just keep them running in parallel. And we will express that pretty much like that. That's the easy bit. The bulk of the work in Mergesort, of course, is in merging. And if you think about it, just the very last merge, the merge that you do at the very end after the two first recursive calls came back, already takes linear time. It has to go over the entire input once. If you parallelize everything before that perfectly, but then this last bit is sequential, you're still at linear parallel time. And so that's hardly better than the n log n time we started with. In general, for PRAM algorithms, your goal should rather be something like logarithmic to a power, or log to the 5th power if you want to go crazy, or something like that. That's a good algorithm. Maybe square root n if you can't get down to log or polylog. But linear is not so great if you started from n log n. So if we want to go beyond that, if we want to go faster than, well, have more parallelism than that, we have to somehow tackle the merge part as well. We have to do that in parallel. And the method I've shown you seems completely unhelpful for that. And the solution will be to solve the same problem, but look at it from a single element's perspective, and then try to do all of that in parallel. That's more versatile than just this application. You can often do that. And it's often helpful also for other kinds of programming. So I think this is a good way to practice thinking of this way. It often leads to more scalable algorithms in a more general sense than just PRAM. For our merging procedure, we can say for every element, it's either in the left or in the right run initially, and we have to find its position in the final merged sorted run. And it turns out that this position can be computed relatively easily as the sum of two things. First of all, it's the position in the sorted output. That's the same as its rank. We've used that terminology before. It's the number of elements that are smaller. That coincides with the position in a sorted array. And there's two types of elements, those that come from the left run and those that come from the right run. And we can just count how many are small in the left, how many are small in the right, add that up. That's your rank in the sorted output. So we can do that easily for one of the runs, namely the one that contains x. That run, as the name says, is sorted. So the position of x there already is its rank within that run. And for the other run, we can use another algorithm to find the rank, and that's binary search. All the way back, Unit 2, we've covered it all. Binary search is just a way of finding, in a sorted list, how many elements are smaller than some other element. Right? You start in the middle, are you bigger, smaller, and so on. You wiggle your way through. And so you find the position where you would have to insert this element if it's not already there, so that the list remains sorted. And that's, again, the rank of this element. And if we have both of these information pieces collected, we can just add the two positions up and move the element there in a second round. OK? That's pretty much it. Here's what this looks in code. It's a little intimidating by the size of it, but all the individual parts you have either seen or they're what it was on the last slide. The overall recursive scaffolding for Mergesort is as we had it before in the sequential algorithm. You first recurse in the two halves. And note here, I used a different construct that we haven't seen before. I didn't want to cross it out. I'm just writing, do these two things in parallel, which means in more low-level PRAM code, you would have to assign somehow to processing. You would have to distribute this to different processing elements. For sorting, I think it's usually sufficient to think of each position in the array having its own little processor attached to it. And so doing this in parallel would just mean the left side is handled by its processors and the right side by that side's processors, and they can work independently. Then we invoke the parallel merge that we'll discuss in a second. And what's left is to copy back our merge method, also the sequential one from unit 3, was merging from the runs into an output buffer. That's why we always pass this second array buffer around. So after merging is done, we have to copy back from the buffer to the array that we actually want the sorted list to be in. And we can do that in parallel as well. Easy. Every processor takes care of one position. That was the easy part, right? That's almost as we had it before, with 2 times in parallel sprinkled in. The interesting bit is the merging. And remember from the last slide, we have to do 2 things for each element. We have to find its position, and then we have to get it there. The first phase, finding the position, is split up in the elements that come from the left run and the elements that come up from the right run, but the 2 phases are intermingled. It was shorter to write it in that way, so you don't need an extra array for storing the target addresses. So this first one is for the elements in the left run. So you do a binary search with your element. And again, we do this in parallel. So every processor does this for its element, does a binary search in the right run. That returns the number of elements that are smaller in that run. And we add the rank in the left run. So R at the end of this is the position where the element should go in the sorted output. And so as a second step, we just write it to that position in the buffer. That was for the elements that come from the left run, and the one for the right run is the same. It's just symmetric. You do a binary search in the left run, and you add the rank in the right run. But the moving to the buffer part is the same. OK? I wanted to show the detailed code for this because I think it's fairly elegant using these constructions in parallel. It doesn't take a lot of code to write all these things out. And there's no really nasty bits needed in this. OK? Any questions on this so far? Let's have a quick look at how well this does. And maybe we should do this in the code. So again, what did I use for colors in the past? Maybe you need to stay consistent. All right, green is time. So if we go to merge, then the binary search is done sequentially, right? I'm not trying to parallelize the binary search, and I don't think it's easily possible. I'm not aware of a speed up for that part. Because binary search, it very much needs to know what the comparison outcome was to decide where to go next. That's a data dependency. It's not easy to overcome that. So that part will take linear time, logarithmic time. Logarithmic in the size of the run that we're working in. But I'm just rounding that up to n generously because it's never longer than that. The rest is all linear, is all constant time. And we're doing all this in parallel. And same here. So we have 2 times log n for the merge as parallel time. That's this part. Then Mergesort itself is a little more tricky because it is this recursive procedure that calls itself. But you can do a simple argument about the recursion tree. So we start with the entire list, and we cut it in 2 halves. Okay, almost like 2 halves. A recursively cut and so on, until you're eventually at individual elements all the way down. And you can argue the height of this tree is roughly logarithmic. That's this height. And on each level, we need to add up these log n cost from merge. But we have to do those. Yes, it's at most log n. Some of the merges are cheaper than that, but half of them need a constant times log n. So it's correct that most merges need theta log n. And so the total time is, on each level we have to wait log n time, and we have log n levels. So it's log squared time, parallel time in total. Now for work, if we go back, it's easy in this case because we don't use any building blocks. We just have to multiply this, what happens inside the loops, with how many times we do the loops. So this merging procedure has n log n time, and that's just done twice. So because of the binary searches, this is not work efficient for merge. We know the normal merge ran in linear time, but now work has gone up from n to n log n. But what we were winning from it is that the parallel time goes down to log n. Again, if you sum this up over all the levels, you can basically just multiply by log n by the height, and you get this bound of n log squared n work. Okay? So is that good or bad? It's much faster in terms of parallel time than any of the sequential algorithms or the simple version where you only recursively sort things in parallel, but then the merge is sequential. Because that still had linear time, and now we're exponentially faster in the parallel time. So if you have many processors, it's definitely better. The work went up a little bit, a log factor, which you may or may not feel. That depends a bit on the number of processors. Now, there is a way to make the merge procedure that I've shown you work efficient, but it's quite tricky and involved. So this is again just for your curiosity. The key idea is something like a blocking trick again. You don't do the full binary search for every element, but only for some of the elements. And you know, for the other elements, their rank must be sandwiched between whatever the next elements are where you did the full binary search. Now that alone is not enough, because you could still have a huge range for some of the elements to search. So it's a little more tricky than that. But that's the idea. You could try to not do the binary search for all elements. But the beauty of this simple code is definitely lost in that process. So if you want a work-efficient parallel sorting algorithm, with Mergesort, it's not so easy to get there. Fortunately, we have another sorting algorithm. Let's also try our luck with Quicksort. First of all, the overall structure is the same. It's a recursive algorithm, and the 2 recursive calls are on completely independent bits of the data, so we can do those in parallel. That's the easy part. And again, if we only do that, it's not much use. We still have the first partitioning round that spends linear time sequentially. Unless we parallelize that, no good speedup is possible. And our code that we've had in Unit 3 for the fast sequential partitioning method is not going to cut it here, because it very much depends on the previous comparisons, how the pointers move and all that. So again, we have to switch perspective to a per element point of view. And so here it's a little trickier than in merging, I think, but overall a bit more elegant maybe. You split again the partitioning process into several phases. A reconnaissance phase where you collect information, and then a second or a last phase where you act on that information. And what is the information in this case for partitioning? We just need to know for each element if it's smaller or bigger than the pivot. So it's a single comparison, no binary searches or something like that. But then from that single comparison, you don't already know where you have to go in the final array, because that depends on all the elements before you. But if you think about that, that's exactly what prefix sums can do. If you're in the group of small elements, you need to know how many small elements are before you to the left in the array. And that's precisely what prefix sums can do for you in decent parallel time. Not constant time, but we've seen logarithmic time. Okay, let's try to also put that in code. The recursive scaffolding is, as before, is even closer to the original code for Quicksort. The only change here is this in parallel. The partitioning method is a little more different. We pass in again. So you remember for Quicksort, it's important to choose a decent pivot element. And so all that we've discussed previously about how a pivot can be chosen well or how to improve on this, that's encapsulated in this choose pivot method, and the same tricks can be played as I've shown in Unit 3. So don't discuss that again. So we have this position of the pivot that we pass down. And so as a first step, we swap that out of the way. Now for all the other elements, that's the first phase here, where we collect information. And this time we don't get around without storing some information in between. So we have this array S, which contains, I think it's S for smaller and L for larger. These two arrays store, is an element smaller than the pivot or not? And so, okay, I'm using this Iverson bracket. So this square brackets around a condition supposed to mean 1 if the condition is true and 0 if the condition is false. It's just a shorthand. So we do the comparison and set small accordingly, and large is then just the opposite of that. We can do that in parallel for each element independently, because it only depends on the pivot element and this element. Then we have these two arrays, and then we compute the parallel prefix sum of those two. Because precisely, again, if I'm in the small cohort and I'm the fifth element from the left that is small, I have to go to position 5 at the very end. In the large cohort, it's similar, but I have to add the offset of how many elements are in the small group to that. So first of all, we just compute the parallel prefix sums. Then we also compute how many elements are small in total. That's J. That will be the position of the pivot. And then we can again work in parallel for the second phase, for moving moving the data where it belongs. And here we do the comparison with the pivot a second time, because that's the most convenient way to know, is my element, is that a small one or a large one? I've forgotten if I haven't saved it. So the cheapest way is to just do the comparison again. So if I speaking is processing element I, if I'm responsible for element AI, I check again. If I'm small, then I look up in position S of I where I'm supposed to go. And if I'm large, I'm looking up in L of I, but I have to add this offset j. This I'm off by ones, like you have to subtract 1 here because we start arrays at 0 and all that again. I hope that the code is correct with respect to all those details. So again, that's the moving phase. And that can all nicely be done in parallel. Okay, is the code somewhat clear? Let's have a brief look at how good this is again. So for the time, if you look at all of those loops, they're all in parallel. So we only have to look inside one of those. And that's constant time. It's just a single comparison and a few memory assignments. And same thing here. That's also constant time. Just a few comparisons and a few read and writes. There's, of course, the parallel prefix sum, which is not for free in terms of parallel time. That costs us log n parallel time. So the overall partitioning procedure, if you look, the rest, that's constant time, that's constant time. It's all constant time except for the prefix sums. So the overall time for the partitioning phase is log n again. And then if we do a similar trick for the analysis as for Mergesort, if we need log n time on each level of the partitioning step, then we can multiply that with the depth of the recursion tree. Now the recursion tree in Quicksort is not quite as rigid and clearly balanced as the one in Mergesort. It's only in expectation so. But I don't want to go into this in more detail. We'll just use the expected depth and say the caveat here is that this is expected case only. So you don't get easily this worst case bound from Mergesort. For that, you would have to pick a really good pivot, which gets us into the trouble of how to find a good pivot. And so I don't think that's easy in parallel. But the expectation bound is fine. And so we get the same result as for Mergesort, log squared parallel time. The difference is in the work, because if we look back in terms of work, all those loops, they're just doing roughly n times some constant operations. So that's linear time, linear work, sorry. The same here. We also have the parallel prefix sum. And now it depends which method for that you use. But we know there's a way to do it work efficiently with linear work. So I might as well use our good algorithm instead of one of the poorer ones. And so the overall work is linear in this case. And remember, that was not so easy for Mergesort. The merging step was also log n parallel time, but n log n work in the version that I've shown you. And that means Quicksort in total, if you again multiply with the expected depth of the recursion tree, you get n log n work. And we know that that's the best in the sequential world as well for comparison-based sorting. So we're work efficient. That was not so easy to do with Mergesort, but Quicksort gets it here, at least in expectation. Now you could ask, is this the best you can possibly go for? For all the natural methods, we seem to arrive at this parallel time log squared n. Is there something magic about log squared of n? Or log n squared, I should say. So this is the typical notation. I don't know if this causes confusion, but what's meant is log of n and then a square, right? It's not something like log of n, sometimes also written with a superscript. Log n to the power 2. Is there something magic about log squared? There's nothing magic about log squared. If you're willing to go to more sophisticated methods, you can actually get down to log n parallel time. It's some intricate variant of Mergesort, but what you have to do for that is basically give up the nice separation of now I'm doing this merge step. When I'm done with that merge step, I'll do the next merge step higher up in the recursion tree. You have to break that all open and kind of start parts of the next merge while you're still finishing off parts of the previous merge. By interleaving things that way, you can improve the overall parallel time. It's a pretty cool theoretical result. I'm not sure if this is realistic to ever be implemented and be competitive. But it's in theory possible to cut it down to logarithmic time, parallel time, and potentially faster on these other variants of the PRAM where you can do concurrent writes. That's one side of the things I just wanted to mention this result without giving you any details. That's beyond the scope. The other part in practice, if you want to implement algorithms, we have to deal with the fact that these things are not PRAMs with these nice synchronized processors where synchronization is basically free. So the practical challenge is to do what we've done, but not break things down into tiny little work packages. And so it's often more convenient to structure code a little differently. If you want to see some really neat and fairly recently designed examples, the Java library has a few that are really nice and well readable, and nothing too crazy in the code there. But they're in a way close to our parallel merge sort, just different way to slice up work packages. All right. I think that's just another way of saying if you were to implement a complicated algorithm that has log n parallel time instead of log squared for the simpler methods, to see that difference, you need a lot of processing elements. Otherwise, the work will dominate. Remember Brent's theorem to convert from work and span to actual time if you have a fixed number of processors. And because here work is still n log n, you need a fair number of processors before that difference between log squared n and log n makes its way through to the final result. That's all I want to say about parallel algorithms for now. Questions on the sorting part? On parallel sorting or the other parallel algorithms? Okay, that brings this part to a close. That's the end of Unit 5. There was a question that we might discuss before we switch gears again. So for the exams, do we need to write pseudocode or something like that? That's one possible task for. Okay, I think I've never spoken in the lectures about this, even though I posted it on CampusWire. You're thinking ahead of time, but I'll post the mock exam and this information this week. It's basically done now. So the exam will have 3 types of questions, and it will be very structured in the sense that there's 5 sections, which are called 5 questions, I think confusingly. 5 sections, and you get the mark is the best 4 out of these 5, right? So whatever the exam paper says is a bit cryptic, but you can really work on all 5, and just the lowest mark will be dropped. You don't have to select. You can work on all 5 if you have the time. That's the one thing. Each of these 5 sections has 3 little sub-questions. And they have nothing to do with each other. It's just the format of the exam has always been like this. The first part is a reproduction question. That's something basically that we've discussed in class or in the tutorials. And I'm just asking you to remember that, or do a very simple kind of apply things you've long known. The second type of questions are application questions. These are like the class tests. You have some algorithm that we've discussed here, but you have a new example that you have not seen before, and so you have to execute the algorithm on this new example or show a technique that we've done on some new example. And the third type of question, the last one, is a transfer question. That's one where you have to think a little beyond what we've covered. You have to puzzle two things together or think a little out of the box. Potentially also, that's why I'm bringing it up here, potentially also design a little bit of an algorithm. Nothing too crazy because you won't have too much time, but a little algorithm that is a variation of something we've seen or uses some component that we've developed for something slightly new. For that, I'll usually ask you to write something that I would call rough pseudocode. It can be even more relaxed than the things I have on the slide. I'm just avoiding to say, just describe your algorithm in prose, because that usually gets long text without any structure and is hard to mark, but also is hard for you to express yourself clearly. So I think some bulleted text with loops and ifs, that's the level of pseudocode I would expect for these questions. There's no specific syntax that you have to follow, but it should be clear and precise what you mean. And we all know that if you just write English language text, there's ample room for ambiguities and vagueness. It's hard to avoid, so I'll try to give you a little bit more, push you in the direction of pseudocode. But it doesn't have to follow a very specific style. Okay, so that's the three types of questions. If you do the reproduction and the application perfectly, you'll easily pass. For a first, you probably have to think about the transfer questions as well. And because it's best 4 out of 5, you have at least one go where you can blow it on one of the questions. It doesn't affect the mark at all. And then it's the sum of the best 4 of the sections. Question? That's for the January exam, the final exam, exactly. Yep. Which is paper-based, in case there were any doubts. You will get the questions printed out. I should bring my own example. I stole one of the from the scripts last time to show to next students what the paper looks like that you write exams on. You've never done the exams in the UK potentially, right? So the process is a bit, it's an exam. I don't think it's very, very peculiar, but maybe it's helpful for you to see. I'll bring that along next time. So it's just separate sheet with the questions, and there's one exam script where you have to write everything. Well, there's a few pieces in the module where I said this is not on the exam. That's the one part. I mean, for revision, the tutorial questions are often closest to just helping you figure out how far you followed in the exams. You can read other textbooks. Sometimes it's useful to hear it explained in some other person's words. And we'll have some more practice questions. So the class tests are literally old application questions from some exams. And I'll have the last tutorial sheet has a bunch of transfer problems. If you want, I can put that up already. I haven't because it discusses things we haven't covered in class. So I didn't want to students click on it, I've never seen this, and run away screaming. It's because we haven't covered it, but we will cover it before you're assessed on it, of course. But if you feel like it's helpful to already see that, I can put it on the website. You've been warned, right? So don't freak out just yet. Right. Okay. Sorry, there's 2 other questions. Okay, Python and OpenMP is, I don't know. Does someone know if Python has some? So OpenMP is for the C or C++ world. I'm not aware that this is directly usable in Python. Python has a library for threads to program parallel things. To be fair, I think parallel programming in Python is one of the parts where Python is not the strongest language that you could have. There's other languages, more recent ones often, that have just profited from the development in programming languages, especially in concurrency. So how do you orchestrate parallel computation? There's been a few innovations since, the late 80s. Python dates back to late 80s. And for C, C++, it was late 70s, early 80s. So I don't think there's OpenMP for Python, but I'm not sure. There's so many packages. In a way, NumPy is often quite similar to the way you program with NumPy is quite similar in spirit to what we've done in PRAM algorithms, because you often also think about what happens to individual elements, and it's automatically scaled up to all the elements in a matrix or even, well, a vector or a matrix or whatever, tensor. It's not necessarily parallelized, but the way you write the programs there, it could easily be. That's why I said it's this element-wise thinking is often useful beyond that. Okay, I'm losing the other half who hasn't done NumPy. Yeah, that's a good question. When do we know when the exam will be? I don't know yet either. It's well, this is centrally administered, so there's some poor person has to figure out how to resolve all the conflicts that people have with exams and rooms. So there's a whole department just timetabling these things, and they will eventually come up with a timetable. But the 2 or 3 weeks in January where it will be. It will definitely be in that period. Unfortunately, that's all I know for now. It'll be in a few weeks. I think it should be decided. You should know well before Christmas. Not that it makes such a ton of a difference in terms of the preparation, but maybe planning your January. I know. I'm not a big friend of this late scheduling, but I'm not sure if we can avoid that. Okay, guys, you got me talking for long enough that it doesn't make sense to start the new unit today. I want to at least show it, because it has today's date on it. Otherwise, I have to change the slides again. That's a good reason, isn't it? So just to advertise for this a little bit, we'll start on Wednesday properly. We'll come back to string matching, but in a different way and a much more exciting way, I think. We'll look at how can you speed up string matching if you pre-process the text. So you're given the text in advance and it doesn't change all the time, but you're looking for patterns many, many times over, but you want this to be much faster. Remember Unit 4, every string matching needed to at least read the text once, or maybe not every character, right? There were a few smart tricks, but you had to basically scan the text, and we'll get around that with that chapter. We'll briefly talk about inverted indices, but mostly we'll talk about suffix trees and more modern indices based on that, which have come a really long way. It's also we get quite close to cutting edge research in this. I think some of the algorithms are from this millennium. I know it's not yesterday. Some things at the end are even younger. Whereas most of the algorithms we've discussed before is kind of old gray stuff in a way. Binary search trees, etc. 50s, 60s, sorting, right, as well. But this is much younger and quite fundamental still. There was a question I would have asked next time. Maybe we can do that. So I can already prepare that a bit. I haven't told you, and of course, is this just, so I won't even pronounce it for you for now. Do you know what that is? Well, I might as well. It's called a trie. Someone thought it's a neat idea to take this as a part of the word retrieval, because it's a retrieval data structure. And then people noticed, oh gosh, if we call this a tree, it's going to confuse everyone, because there are already so many trees in computer science. So let's just pronounce it trie, but stick to T-R-I-E. Good idea? I don't know. But did it stuck? Yes. Did it stick? Yeah. Okay, I guess we'll go slowly over tries on Wednesday. Okay, we might as well do the Q&A. I think I covered this. It's all on paper and offline. You will definitely receive some marks eventually. So we're looking at this now, but it usually takes a bit of time, because we have a policy in place that assessments should have a certain average mark. So the other problem is, this is good to mention again, I'm away next week, so we'll skip the lectures. I mentioned we have this 10 lecture weeks and 12 term weeks, so there's always a week that we can move around, and so this is your reading week. Now Ben might write on CampusWire what he does with the tutorials. There's no tutorial sheet for next week, but he might use that slot to give you a debrief of the Bamboo assessment, and you can ask all your questions about that one there. So maybe we'll get the marks till the end of next week at least. It depends how much controversy there is with the scales. And that's a very, very personal question. I think it depends a lot on your preparation. I mean, there's no exam that's not stressful in a way, right? That's part of the thing. It's, to put it positively, it gives you the adrenaline you need to focus for 2.5 hours straight. It's 2.5 hours, by the way. But that's the total time. You don't have to stay for all that time. I just don't like exams that basically give, easy problems, but as many of them that you get the distinction between the different grades for how fast can people solve them. I'd rather give you more time and make the distinction between there's easy problems that most of you will do fine on. There's application problems that you can practice, and there's transfer problems where you have to show understanding. But you can pass with the first two categories, and the last one distinguishes the marks. So that's why the 2.5 hours, I mean, from past experience, most people stayed till the end. But you probably could have finished earlier. It's just, yeah, if you know, oh, I could improve, then you don't waste the time. I think I've had students pass and go after half of the time. It's always a cool statement to get up and go after half the time. I think the exams have to be stressful. There's no way around it. It's a high stakes exam. I try to split it a little bit with the class tests and take some bits of the mark off the final exam, but it's not zero. All right. Last one, because I like that one too. Oh, I didn't want to take it off. The question was, will the class test questions come up on the exam again? No, I like the question.